Welcome to Lesson 4, example number 8. And it asks, actually it gives us a 16-foot long column of A36 steel, which I didn't. Let's go ahead and put yield stress. It's 36 KSI. And it supports an axial load of 250 and a moment of 80 foot kips. And this is what it looks like. I guess it could be part of a, let's say, a framed structure of some sort. You know, let's say it's a frame structure like this or something. And don't quote me on this, but it could be a frame. Something in the end, something's inducing a moment up here, and something is an axial force. So you have some weight going down, or some live load going straight down that axial, right down the axis, right there. And then we also have the moment at top. All right, and they said that we have a K of 1. So that's why we said, okay, assume it's a pin, but that's not 100% correct. You just say, you know what, we have a K of 1, but for simplicity right now, you can kind of assume that it's a pin. And I'm not going to get into that right now. The Ks are really subjective, but they kind of give you some guidance on that table that you've seen with the option E or A through F or something like that. Anyways, they've given us the K. And what this is combined. It's axial load, which is compression, is the type of axial, plus bending. And we call that a combined loading. Combined, that looks good enough. And when you do this, it sounds like there's a bunch of different ways you can do, and I'm gonna try to do a brief explanation right here of what they're doing. It's called a first trial approximation. So let's I'm gonna try to explain what first trial means. You've got an axial load, correct? And I'm gonna say it's way out here. This moment is going to push on it like that and create that type of shape. I hope that makes sense to you. That moment's going to do that. It's going to bend it. And that should be intuitive by now. Also, when you add this axial load, this compression force, it's going to make it buckle as well. And buckling is it's not as simple as you think, and you can look into your structural books if you want to look up buckling, and they'll try to explain why or what's exactly going on in this buckling, and it's not the easiest thing to know. Just remember how to do it as opposed to what exactly is the derivation of that equation. But anyways, so it's going to pop out like that. I hope both things are going to be doing that. The moment's going to make it bend that way, and the buckling force is going to make it worse. And depending on how much moment this is, it's going to be less. You're going to be able to handle less axial force, and I hope that makes sense. Is the more it's going to hurt you. It's going to be buckling sooner the more M you have. So that's really, really hard to figure out. It gets to be extremely complicated, and you can do. Once again, the complicated is not this first trial approximation. And to do anything other than this kind of an approximation takes a computer program, and it will take that computer program sometimes hours to complete. So, and we will go into more further analysis on why that is later in other videos, explanation videos. But for right now, let's move on to say that this, because that'll make that move, it makes. And I kind of said I'd be done, but I won't. Because this moves right here, this deflects, it's going to make this P is going to be worse, and it's going to do that. So it depends on how much it moves. It's going to get worse, and then the more it moves, the worse it's going to become. I hope that makes sense. So it's kind of an iterative process. It's not kind of. It's definitely an iterative process, which gets just a Not a fun thing to go through. So they've made some approximations, and that's what we're going to do. And in this approximation, we're doing the same thing that we did in the wood, which the main equation is, you can look at it as, we want to do this P, the P load, plus, actually, the stress is going to equal P over A, which is your axial, plus M over S, M of, let's say M of X and Y, S of X, and your strong axis moment over your strong axis section modulus, and then your weak axis over that. And you're going to add all that together. That's essentially what you're doing, and I hope that makes sense to you. You're going to add this stress, plus if you're bending, you're going to increase the stress on the compression side, and obviously it will decrease the stress on the tension side, and the same over in your other direction. And that's the general thought that we're doing. But they've also come up with an easier equation, a simplified way of even going about this. And what it wants to do, and what we're doing this simplified approach, is we're finding a P effective, and equals P naught, or just your axial force, plus your moment in the x direction, or over the x axis, and your strong axis, times M, plus My Mu. And this is a factor taken from the column load table, and we're not going to use that right now. It doesn't look like we're going to have to. So in this situation, we don't have any moment in the y direction, so we're going to go ahead and cross that out. This is what I would call a moment magnification. And that the whole reason you're using this M factor is because you're magnifying that moment because you have the buckling issue. That's what this is pretty much accounting for that. And typically these are pretty conservative, if I remember correctly, to make sure that you're not going to buckle. So this moment magnification is probably going to be more than that iterative process of a second order approximation or a second order analysis. Alright, so let's go ahead and solve for P effective. And in this, you also can use tables to approximate this M, and that's on page 3-10, and it says table B, and it says values of M, and it's approximating a value of M. And then they said that we want to use W10, so you go to the left side, you can see W10, and you also know your KL, and it says in foot. So our KL equals 1.0, and then our L, what was our L? Our L, let me go back to the equation, I didn't write it down, is 16 foot long. Alright, so 16 foot, our KL equals 16. So we go in the table, we go down 16, we go over from W10, and it looks like 2.2. You use the top one, and then its subsequent approximations is 2.4, but we're going to use the 2.2. So M equals 2.2, and that's from table B. So our PO is 250. 250 kips plus 80 foot kips times 2.2, and then we'll go ahead and solve for this. And remember, if you have a moment in the y direction, you'd actually also do the my times the moment magnification times u. We assume u is 3. Is let u equal 3, I think, is what's typically done. But since my is 0, we do not have that. And then we go ahead and solve for this, and we get 250 plus 80 times 2.2 is 426. 426. Alright, and that should be in kips. I know that's not 100% clear, but since it's a P equivalent, that's what it's doing. And then we enter this number right here, the 426, into the table on page 329. I know this isn't horribly intuitive, but this is why you got to know your Steelbook. And on page 329, you have columns, and it's W10 columns. You can see that up in the middle. It says designation W10, and you go down and you say, okay, well, my KL we know is 16, and we want to go over from 16. And we also, since we know our W10, we don't know what foot we want, so we need to go over from 16 and go over until we find something that is greater than 426. But we don't want to go anything less than that. So we go over from, we're at 16, we go over 5. And remember we have 36, Fy is 36. So if we go too far to 88 pounds per foot, W10 by 88, that would be 417, which is less than 426. So we want to go back over to 16. It goes over to W10 by 100.
What the hell?
All right, and I hope that makes sense. But that is your answer. You want to use a W10 by 100 whose tabulated allowable axial load is 476, which you could say P A equals 476 kips, which is greater than your P actual. This is P allowable equals 426. And that means we're good. We have a greater capacity than we do have a load, and we can move on. All right, thanks. I hope this helps.